Okay, thank you for coming. Sorry we're a little slow on getting set up. It's our first time having food, so that was an entire hassle that we were not used to. Today's event, we're going to be talking about quantum machine learning. It's not expected that you're going to be an expert on this, obviously. The first thing we're going to go through is just sort of an introduction to what machine learning is, and then talk a little bit about the differences between regular machine learning, so-called classical machine learning, and quantum machine learning. And then we'll get into a couple sort of examples of quantum machine learning algorithms. And then, questions, of course, at the end. And there's at the end of the slides, just sort of a list of resources for these topics. So once we send the slides out, you can go click on any of those links to get more information. So let's start with what is machine learning, which is also called ML. So this is a nice diagram that people have probably seen before. It's all over the internet. It sort of just shows the grouping of topics between artificial intelligence and machine learning. They're generally kind of thrown around to be the same thing. They're technically kind of not, but nobody really cares. So artificial intelligence is sort of the super group, and then under that you have machine learning. And under machine learning, there's these two topics, supervised and unsupervised. And there are some things that don't fit into either, but broadly, those are the two topics. And that's sort of what we're going to be focusing on today. So the definition of machine learning is it's sort of algorithms that take in data and learn certain features with the goal to generalize to other data sets. And there's sort of four key things that I want to, four key terms in that definition that I want you to look at. So there's learn, and that's basically just the process that the machine learning algorithm uses to iteratively do computations. Features are just characteristics of the data set. Generalize is being able to apply your machine learning algorithm to other data sets. And then the data set is just the actual numerical input that you're giving to your algorithm. So we're going to go a little bit more in detail to each of those four terms. I'm calling it the four key terms. So to start off with learn, this is really sort of the brains of the machine learning algorithm. All of the really key decisions in how your algorithm operates and what you're trying to get it to do comes into play in how you design it to learn. And they're typically sort of subcategorized based on their learning method. So some common examples of this is in supervised learning, you have something called gradient descent. And this is just basically the way that it iteratively updates parameters. There's also genetic algorithms, which is, of course, modeled after evolution in biology. And unsupervised, you have things like k-means or autoencoders. And across both algorithms, or both supervised and supervised, you have things like loss function choices. And there's not a great graphic for this. I tried to make this sort of flowchart, and this is about as good of a picture as you can get because there's a million different ways you could have your machine learning algorithm learning. But in general, you say like ready, go to your computer, and then it gives you a bad guess for its answer to your machine learning problem. And like 1 in a zillion chance it gives you the perfect answer. And if it did, that would be crazy. But most of the time you're going to get back and you're going to say, here's some data points, fit a line. And it's like, oh, what if I put a line like way over here? And it's like, nope, that's not good. And it goes and it computes, like it does some math and it says, oh yeah, that guess was really bad. And then it tweaks some of the parameters it used to make the guess. And then it makes a slightly better guess. And then it goes back and computes how bad it is and makes a slightly better guess and so on and so forth until, hopefully eventually you get something that actually works. Okay, so that second term, features. Features are really just any characteristic of your data. And really the complexity of the data and therefore the complexity of the machine learning problem is directly related to the complexity of your features. Really common way to see this is just like the visual shape. If you were to plot your data, what does it look like? But other things is sort of like the number of parameters in your data set, the density of data points. And just sort of as an image here, there's like these two different graphs. They're both like 3D scatter plots. And they both have features, but the one on the left, there's a very clear, it's easy to describe. It's like, okay, this feature is you sort of have like a Gaussian that's centered around, whatever that is, 5 on one axis and 15 on another. And it's like, okay, yeah, sure, that's not too bad to describe. But then the one on the right, like it's sort of all over the place, and there's some blue dots on the bottom left corner, but there's also some in the top right, and then it's kind of like magenta in the top right, but there's also some orange. And so it's really hard to describe in any kind of meaningful way the shape of that data set without getting really specific about what each point looks like. So you would say that the data set on the right has much more complex features than the one on the left. Generalizing. So generalizing is, like I said before, it's just the ability for any machine learning like model to be applied to other data sets and still work. And this is really the main reason people want to do machine learning. It's basically like you get some data and you train a computer, you have it learn to do something, and then you can turn around and use it on completely different data and still get some meaningful answer. And at minimum, this is really between like data sets of the same thing. But sometimes it can extend to other things. So I have sort of two examples of those. I call them less common examples. So you can imagine like if you train some supervised machine learning model, and I'll get into what that means in a couple slides from now. But if you train a model on like 2018 stock market data, then maybe you say that the generalization is that it works good to predict stuff in the 2020 stock market or 2022. And that's a form of generalization. But another form of generalization is there was this machine learning algorithm that like this shop in Japan basically had, so that they didn't have to have any cashiers. People would just sort of show the bread that they were buying, and it could scan it and just based on the picture of the bread, know what bread it was and how much the people owe. And then they found completely randomly that it like worked to diagnose cancer. And so that's a different form of generalization. Like it's a completely different data set, but it's still super powerful because it means that you can change it. You can take it from one place and put it towards a different problem. So here's like a super simple example of generalization. You could imagine sort of the image on the left. We've trained this, like say it's a support vector machine, to differentiate between the blue dots or the blue X's and the red X's. And it, it gets it a little wrong. There's a blue X on one side and a red X on the other, but in general, it does a pretty good job. The idea of generalization is basically, okay, I come in with this yellow X, and it's just yellow because I haven't told the computer, what it is yet. And its job is to then tell me what group it belongs to. And in this case, say it belongs to the red X, and the computer would get that correct, that it does in fact belong to the red X group. And sort of this last one we're going to talk about is data sets. And so, like I said, this is the actual thing that you're giving to the machine learning algorithm that it's then using to learn off of. And there's sort of a couple words that are thrown around for data sets. The ones I like to use is events and parameters. And for supervised machine learning, there's also these things called classes. And some common examples of these is like the MNIST data set is a super classic example of machine learning. It's basically like these hand-drawn numbers. And then the idea is you give the computer a picture of this hand-drawn number and it tells you what number it is. And then, Large Hadron Collider data, just like particle physics data, at which point you have different sort of particles and they're detected with different kind of measurements, whether it's energy or momentum or position. And for events and parameters, really the way you can think about it is you sort of have this like table, and typically you'll put sort of events on the row of your table and parameters on the column. And you can sort of think of the parameters as the dimensionality of your space. If you were going to like plot it in a graph, each parameter would take an axis, and the events is an individual data point. So each data point has some value on each axis, and you plot it. And so here I just put some random numbers and then a completely unrelated graph, and just basically said, let's say parameter 2 goes to the z-axis, parameter 3 is y, and parameter 1 is x. And then you just do that for every one of your data points, and that would be how you could visually show your data. And I'll sometimes use data points. But data points and events, as far as I'm concerned, mean the same thing. Different people might say something else. So finally, we're going to talk about the difference between supervised and unsupervised machine learning. So supervised machine learning, the goal is to basically take in classified data and learn how to classify that kind of data based on the data set features. So classified data is they're data sets that on top of that table I showed before with events and parameters, there's some other sort of non-parameter values associated with each event. And that's the class or classes of that event. And the goal of this model is to the goal of the supervised machine learning is to provide a model that can differentiate between classes only based on the parameters. So you sort of use the classes as like a check, the check on how good the computer does. So here's an example of a support vector machine, which was showed earlier with just a line, but you can do SVMs with higher order stuff. And basically, like what you have here is you have this giant scatter of plots, or this giant scatter of data points, and some of them are red and some of them are blue. And what you want is you want to be able to build a line that differentiates between the red and the blue dots. And so what you're trying to do is pretty much just fit the boundary between those. And then the idea is I can come in after I've built that line, which sort of ends up looking like an S curve. I can come in with a completely new data point and say it's sort of in the top half up here. I could come up with a completely new data point, and then the algorithm could correctly tell me that it belongs to the red circles rather than the blue X's. And vice versa. If it was below, then correctly tell me that it belongs to the blue X's. So unsupervised data or unsupervised machine learning are algorithms that take in unclassified data. And the goal is to sort of learn some classifications. You're trying to learn something new about your data set. And so the data sets only have parameter values. There's no non-parameter values like there are in supervised learning. And like I said, the goal is to learn something new about your data set that you didn't know before, like new correlations between parameters. And a super classic example of that is k-means. And so essentially what this algorithm is doing is it starts out with, the k is just basically how many groups you're going to form. In this case, it's 4. And it starts out, once it loops back, it starts out with really bad guesses. It just draws random boundaries for where this 4 groups are going to be. And then what it pretty much does is in each group, it calculates where the mean of all those data points are. And then it shifts, like you can think of the position of that boundary, like the dark brown. It shifts it to that new mean. And then it does this for each grouping. And then it calculates the mean again, and then it shifts again, and it calculates the mean again, and it shifts again. And what it essentially does is it looks for clusters and it groups things by cluster. So you can see obviously in this data set that you have like 4 clusters here, you have 4 groupings. And so what a human would do is they'd say, yeah, you probably group this together, that, and the bottom right one. And that's all that k-means is doing as well. Okay, so that was like lightning overview of machine learning. Before I go on to talking about quantum machine learning, are there any questions about that? I can go through anything again. If it was not specifically covered, I could probably try to answer it. Yes.
So with the classified, your other non-parameter for determining would be the fact that it's red or blue.
Yeah, exactly. So in this case, like the class would be whether it's a red circle or a blue X, and the parameters would be its XY position. So we tell the computer the parameters, and it's trying to learn to differentiate classes based on those. Yeah.
What was the third? The third one was like features.
The 4 terms thing.
Yeah.
Generalization, which is it's just sort of important because that's like the entire reason that anybody wants to do machine learning, is the idea that you can make a computer really good at one problem, and then you've solved a whole bunch of problems with that. Because if you spent like all this time in like writing this algorithm that was really good at one problem and not good at anything else, you probably could have spent less time just solving that problem. Instead of like trying to make it generalized. So that's just sort of important because that's the whole reason anybody does this. Any other questions? Okay. PowerPoint is slow. Okay. Classical machine learning versus quantum machine learning. Okay, the definition of quantum machine learning is broadly, it's really any machine learning algorithm that includes a quantum computer in part of the computation. And it doesn't have to be the whole thing. It just has to be even one small part. And a lot of the classical machine learning algorithms have quantum machine learning counterparts. So I had mentioned like support vector machines, which is sort of like differentiating between multiple groups of the line. There's a quantum version of that. There's autoencoders, which I said is an example of unsupervised learning. There's a quantum version of that. There's like a quantum k-means, which is technically called just q-means. And there's these quantum machine learning algorithms can use both quantum data or classical data. And so quantum data is like, it's the output of a quantum process, and you just feed it directly into the quantum computer in this sort of quantum state. And that sounds confusing. That's because it is confusing. And it's really hard to do because you obviously have to, like, you have some superposition, some basically really hard to maintain data, and you have to somehow measure it from one system and encode it into your quantum computer without breaking the superposition. So I don't think many people are doing it right now, but it's a good avenue. It's thought of like as a place that quantum computers could easily surpass classical computers for machine learning. And then classical data is the typical stuff that we're used to. So just like the regular table that I showed before as data sets. But you know, typically because of how error prone our current day quantum computers are, the typical flow for quantum machine learning algorithms is you have some sort of classical preparation of state. So you basically have a regular computer that encodes, says, okay, quantum computer, you set this qubit to this qubit to that. And then the quantum computer does some computation. So it adds qubits together, or you know, does whatever, makes a superposition, collapses it. And then after you've done your quantum computation, you then collapse everything back to a classical state as your sort of readout. And then you do some like computation of loss, as like I said before, some sort of basically like how bad is this guess? And then you use how bad it is to feed back into the classical preparation of state, which feeds back into quantum computation, and so on and so forth. And this is just sort of important because it's like, even though I said, yeah, you know, you could run a quantum machine learning algorithm with all of a quantum computer, or only just part of it could be on a quantum computer, but realistically these days only part of it is ever run on a quantum computer because they're just not good enough yet. But in the future, potentially this could all be done on a quantum computer. And so this is really just here to hammer home the idea that those 4 key terms I showed before are like identical in quantum machine learning. And in fact, just like squint your eyes, and if someone told you they had a machine learning model to do something, there's no reason for you to think that it's a classical machine learning model or a quantum machine learning model. Like abstractly, in terms of the math of what it's doing, they are pretty much exactly the same. So any amount of experience you have with regular machine learning is also experience you have with quantum machine learning. You just haven't run it on a quantum computer yet, which, you know, does make a difference. So the impetus behind quantum machine learning is really the same impetus behind any sort of quantum computation. It's the idea of quantum advantage. And quantum advantage is just basically the metric that people are using to compare classical computers to quantum computers. It's kind of difficult to say exactly what the definition is, but it's like broadly, you have to be able to prove that you've done a problem on a quantum computer that's extremely difficult to do on a regular computer. So like everybody throws around examples like super high, super big prime number factorization. There's also stuff like, you know, perfect optimization of the traveling salesman problem, like things that we just know you just can't do because it would take millions of years. If you could come up with a way, you're like, hey, I ran this on a quantum computer and it took 2 seconds, then that would be quantum advantage. But the specific boundary between, like, you know, if it takes 100 years, is it still quantum advantage, or does it have to take under 50 years? I don't think anybody has a great answer to that. And the other important thing to know is that in general, advantage is really only proven for specific problems. It's really hard to prove for general classes of problem. So you'll have a lot of somebody saying like, oh, like we're thinking we could do quantum advantage on this thing. Like there's an example of a quantum machine learning algorithm that was like, it's faster than classical machine learning algorithms if the computation you're doing is like the modulus of the log, and you're like, cool, when am I ever going to use that? But in that one circumstance, it is better. Okay, so the pros and cons between the quantum machine learning and regular machine learning. And you'll see that it's structured this way because the pros of one are really the cons of the other. So classical machine learning pros, it's simple documented implementations. If you like want to know how to do something, you can Google it and you'll get a million different YouTube videos and a million different websites explaining to you how you can use X algorithm to do whatever it is that you want to do. And there's really well understood limits. Like it's pretty common that you'll try to do something and you'll say, oh, this didn't work. And then you'll go online and you'll see somebody say, yeah, that it just does, like whatever algorithm you're using cannot do that type of problem. You're like, okay, well, good to know. On the flip side, the cons of quantum machine learning is that it's very rarely sort of implemented. So if you're trying to do it right now, it's going to be a lot of having to figure out on your own how to get any given problem to work in quantum machine learning. And there's poorly understood limitations, which is annoying because at any given point, it's sort of unclear whether if something is going wrong because of you or because it's the algorithm just can't do that. And then classical machine learning cons, it really falls apart at high dimensional data sets or complex data. And it can't really utilize quantum data, obviously, because it's classical. Versus the pros of quantum machine learning is it has a potential, keyword potential, to succeed even while using complex data, and you can input quantum data directly. And just to go through those sort of four things more explicitly. So like I said, implementations, like current quantum computers are really error prone. So any machine learning algorithm you're going to try to do, you have to be like very careful about the way that you code it, or else you're going to get complete garbage out. Limitations, if you don't know how good or bad a program is and you try to debug it, you're going to be in debugging hell because you're not going to know whether your code is wrong or like the quantum computer is wrong, or whether you should just like quit your career and do something else. And complex data, like so-called big data that everyone sort of talks about now, in general for classical machine learning, you have to reduce it a lot just to make it feasible to run. And there's a potential that quantum machine learning could allow you to run it more directly on the full big data sets. And then, like I said, quantum data, you can input directly to a quantum computer, but this also requires like really good quantum sensors and really good being able to maintain a quantum state. Okay, so that was sort of the comparison between classical machine learning and quantum machine learning. It was not super technical, it was sort of more high level. Are there questions on that? Yes.
Why is classical machine learning not so good at big data? Is it like the problem scale such that it just gets worse?
Yeah.
Exponentially or whatever?
Yeah, exactly. It's as you get to more complex data sets, I mean, like there's a couple reasons. There's the simpler answer of just like the traveling salesman problem, even if it's a simple problem. Oh, okay. You don't know what the traveling salesman problem is. Okay. Say you have like, there's a salesman and he has to go to all these different cities and the cities are connected by roads, but not every city is connected. And he wants to know the shortest path to get to hit every city. And so any sort of like classic optimization problem like that, you can get close to the answer pretty easily, but to actually get the answer for like classical computers is basically just running it for hundreds of thousands of years. So that's one reason that you could say they're not good with big data, because at some point it just gets, the runtime is too long to be feasible, even though the actual thing they're doing at a small scale is completely doable. The other thing is if the features of your data, even if it's not particularly large, if the features are sort of complex, then you're gonna have a really hard time doing machine learning on it. I mentioned gradient descent as one of the ways that you can have sort of like a learning process. And what that basically means is like, I'm gonna go all the way back to the image that I had for features. Yeah, here. Okay, so the gradient descent is basically, say this is your, like, you have something called like a loss function, which is, like I said, it's just the mathematical encoding of how bad the computer is doing. So like, say you're here, you want your loss function to be minimized. You want your computer to be doing as good as possible. And your computer gets that it's here right now. Oh God, it's gonna click on the screen. So your computer gets that it's here, and basically what it's like, it wants to get to the smallest value of loss possible. So it computes the gradient of this loss function at that point and goes opposite the gradient, because gradient is steepest ascent and you want steepest descent. And then it just moves a little bit. It nudges the parameters to move a little bit this way. And it just does that iteratively over and over and over. That's like a super, super simple way that people implement machine learning, is with gradient descent. But you can obviously get into this problem. You say, well, what if I get to like a flat part of my data set? What if my data set is like Swiss cheese? It's just like a flat plane, and then there's holes or like little peaks and valleys in it. And it's like the gradient descent can't really do anything to help you there, because it gets to a flat place and it's like, oh, I'm at a minimum. And it's like, no, it's not. It's just on what we call a barren plateau. And there's a potential that quantum computers could be better at dealing with these really complex data sets. But that's, again, sort of hard to prove. Yes.
The difficulty in proof is that we don't know if we hit it or if we're just at the hole, right?
For barren plateaus?
Yeah, we could be at a barren plateau or we could be at a minimum. Right?
Yeah, no, exactly. Because the way that you do it is based on, if you're just looking at the gradient, then yeah, you're basically stuck in, it's like, it keeps getting back to the same value. And then it thinks that it's at a minimum, which like it kind of is, but not really. Yeah, go ahead.
Why not simulate it anyway, where you just pick a different starting point?
Right, and that's basically the only way that people have found to deal with barren plateaus, is you start at a different point and you just run this over and over and over and hope that eventually it randomly starts at a spot that it can easily get to at least a local minimum, if not a global minimum. And the other thing people have done is like, you can say, if it for some reason finds that it keeps getting the same answer over and over, you could have it jump a certain distance away. And the idea is that if it is in a local minimum, it'll jump, go higher, and fall back down to it. But if it's on a flat plane, it'll jump somewhere else, and maybe it'll jump close to a local minimum, at which point it can gradient descent its way back down. And like, it's not for sure that quantum computers are going to be able to completely erase that. Nor are we even certain that they're going to necessarily be better with dealing those types of problems. It's just that because we don't know, there is a potential for it. And as the world gets more complex, because people collect more data on everything, we're going to have this problem more. So there's sort of like a incentive to look for any kind of optimization we can find. Other questions? Yeah.
I know, like, I don't know anything about like quantum.
Yeah, right.
That's like, what exactly is quantum data, and like, why is it better than classical data?
Right. So it's not, I don't know if I'd necessarily say it's better. It's just more like it's different. And so in this case, quantum data could be useful if you had a quantum process. So in the regular world we all live in, things they're classical things, and that's why we have classical equations to describe them. So it would sort of not make a whole lot of sense to care about quantum data. But you could imagine if you were trying to do some measurement of something on a quantum scale, like of some particle, that is inherently quantum mechanical. And if you wanted to do some computation on it, if you could somehow keep your quantum state through to the computer, there's a potential that it would work better, just because they're quantum computers, they're using quantum data. So if you could feed the quantum data directly to it, rather than what we have to do now is like, you make some sort of quantum measurement and then you record it as classical data on your hard drive, and then you send that data to some really rich person that has the quantum computer, and they encode it on their quantum computer as quantum data. And it's like there's this middleman of classical. And so if we could remove that, the thought is that maybe quantum computers would be able to perform a lot better. But yeah, it doesn't make sense to use in like regular things, except for, I should give one more caveat to that. There's a paper that came out recently talking about encoding data as classical data as quantum data. And so maybe you could say that you could reduce your dimensionality, like reduce the size of your data set by encoding it as quantum data without actually having to like remove parameters. So it's like lossless compression versus lossy. Yeah, you don't seem satisfied with that answer.
I don't know anything about like stuff. So,
Yeah, I mean, you're definitely right to like question the usefulness of quantum data. And truth be told, I don't fully understand what it is. Like I've done a little bit of quantum machine learning stuff, but I've never used quantum data. I just know like people that I've worked with throw it around as like, oh, this is gonna come up, and like you squint your eyes and it kind of makes sense. Like quantum computers would be better with quantum data, but yeah.
What's the difference between machine learning is some kind of algorithmic technique you're trying to tackle a problem with?
Yeah.
So how does changing the hardware change, I guess, the problem solving approach?
Right. Right. Good question. So it really comes down to, well, there's like two pieces. One is because current quantum computers aren't that good, you have to solve the problem in sort of obtuse ways, which I'll get to in the QML example. Maybe I'll put this slide up for now. You kind of can't, because like regular computers are advanced enough, you pull up a Python script and you type out whatever you want and the computer can do that thing. You'll try to do that on a quantum computer, and sometimes like you'll do the equivalent of typing a command, like you type a print statement and it's just like, sorry, I can't do that. And then you just have to work around that. So it changes the ways that you have to sort of like mathematically encode your problem. Even if it's sort of equivalent math, you have to say it in a different way. But the big reason that quantum machine learning would be different than classical machine learning is the same reason that people think quantum computing could be different than, like quantum computations could be different than classical computations, which is just the idea that there's a potential for really hard calculations on regular computers to be able to be performed on quantum computers.
So the hardware, so just the hardware advantage.
Yeah, no, exactly. No, yeah, the theoretical framework, the machine learning framework on the top is like basically identical between the two. And that's what I was trying to, that's what it really, if you get one thing from this like talk, get that if you know anything about machine learning, you can almost immediately apply that to quantum machine learning. You just have to like learn some libraries for how to interact with like specific quantum computers. But the actual like headspace that you should be in and like the math that's behind it is pretty much the same. So here's the first example of a quantum machine learning algorithm. It is near and dear to my heart because I've worked on it for like a year. It's called QAMLZ. That stands for quantum annealing or quantum adiabatic machine learning with zooming. And what QAMLZ is it's a binary classifier built from a linear sum of weak classifiers, and then it's run on the D-Wave quantum computers. So we'll break down sort of what those key terms are. Binary classifier means that it's supervised machine learning, and then there's two data classes. So in that example I gave before with like red circles and blue X's, that's a 2 class, that's binary classification. You can imagine, if you had a yellow triangle, it would then be like 3 classifications. Weak classifiers are basically just really, really crappy machine learning stuff. They just sort of look at one parameter and depending on only that one parameter tell you what class they're in. So again, in that example before, like there's 2 parameters there, there's the X and the Y, and you could imagine that a weak classifier would just look at the X and it would say, oh, it's less than 0.5, it must be red. So they're obviously not good. They're horrible, they're like terrible. You would never just use a weak classifier. But the idea is that you can, in general, just sort of add up weak classifiers and build an actually pretty robust full classifier. And that's what that linear sum is for. It just means that you add up the weak classifiers and then they're weighted on, -1 to 1. And then you just combine them together. And those weights on of the weak classifiers, that it's on that range, -1 to 1, is the goal of the machine learning. Like that you're going to add up all these weak classifiers, and the goal of what you're actually trying to optimize is what these weights should be to get the best, most robust boundary. And then the fact that it's on D-Wave matters because there are these special types of quantum computers called quantum annealers, and that really comes to head with what I was saying before about you have to like encode your problem in a special way because they can only handle certain problems. So you have to like write your problem in a specific way and then transform your data to be in a way that they can read. And there's all this sort of like pre-processing that you have to do specific to the fact that it's on a D-Wave computer that you might not necessarily have to do if it was on, say, like an IBM quantum computer. And again, just sort of plugging my own work, this is how easy it would be to run QAMLZ. You have to import the package, it's on PyPy, and then you basically just make an environment, which is just your data. You just pass your, the X train is like that full table I showed before of events on the rows and parameters in the columns. And then Y train is the classes. So it's like for each given event, what class is it in? So you just make your environment and then you call like a configuration, which you can change the hyperparameters, which is essentially all the little ways that you can meddle with the way that the algorithm is learning. And then you just say model.train, and then it goes and does its thing. Here's an example of some data that QAMLZ got. So there's a lot of stuff going on here, and like you don't have to fully understand it. This is just kind of to compare classical machine learning with quantum machine learning. QAMLZ is the blue dashed line, and CAML, which is there's an original algorithm, CAML, and then people added in the zooming part, the Z. So CAML is the black dash line, and QAMLZ is the blue dash line. The red dash is simulated annealing, which is what you were talking about earlier. And it's basically a way to just simulate what quantum annealers do, but on a classical computer. And then DNN stands for deep neural network. XGB is like something boost, I don't remember exactly. But basically this is just to show how some quantum machine learning algorithms compare with classical machine learning algorithms. I'll get to your question in just a second. I just want to say one more thing. The key interesting thing here, quantum machine learning algorithms kind of outperform classical ones at really low training sizes. And this is not just particular to this one. This is a thing that people have seen in a lot of different quantum machine learning algorithms, and we don't know why. And figuring out why might be important to figuring out how they work and where they fit best in sort of the machine learning process. But yeah, that's sort of the important thing from this graph I want you to see. Go ahead.
What are the Y?
Oh yeah, sorry, AUROC, it's area under the ROC curve, and ROC stands for something characteristic. It's basically just an accuracy score. You can just think of it as an accuracy.
Okay.
Like out of 100 percentage-wise, how good or bad is it? Where 100% would mean like it correctly classifies everything all the time. And 0 means that it's like crap. So the other thing to note, because this is binary classification, technically random chance would get you 50%. So none of these are very good. You're at about 2/3. But you know, such is life. So the other thing that I wanted to bring up was, I talked about quantum k-means before. A specific implementation of that is q-means. And that's a clustering algorithm, and it has those alternating phases of labeling and averaging. And because it's quantum, there's sort of added noise. So the k-means before was the one that had like, there's the 4 boundaries, and then it shifts the boundaries around depending on the mean of all the points that are in each boundary. And that's sort of what the clustering means. It just means that it's trying to find giant clusters of data, and it's going to give all those clusters, every data point in that cluster, the same class. And then the labeling is just that at each step, it says all of the data points in a given boundary are of class A, and then a different boundary, they're of class B. And then the averaging, it just basically says, okay, out of everything that's class A this round, where is the mean of those data points? Okay, I'm going to move the mean of my boundary to there. And then I go back and I relabel because I've shifted my boundaries. So they're at different data points are in different classes now. And then the noise is just to say that quantum computers have all these errors. So at any given step in the labeling or averaging process, they basically added in noise. And that's important. I'll get to your question in a second. That's important because they didn't actually run this on a quantum computer. They ran it on a classical computer. They just simulated the quantum computing by adding in this noise. So it's sort of like noisily labels, like if there's a point that's close to a boundary, sometimes it would give it the wrong label, and noisily averages. So it computes an average, but then it says like offset this average by some small amount. And that was just sort of how they were trying to simulate the quantum computing. Go ahead.
Just with the clustering, that would be kind of like on one of the previous slides, like that like graph or whatever, where like all those boundaries.
Yeah, no, yeah, exactly. And that one is k-mean. So this is exactly the, well, I shouldn't say the, because there are probably other implementations, but a implementation of k-means on a quantum computer. This is exactly a quantum allegory to that visual GIF that you saw before of the different boundaries shifting around. And then here's just another example of data. So the red line is k-means. So it is exactly the same as that algorithm that was shown before with the shifting boundaries. And then the dashed lines are different versions of their sort of quantum algorithm version of it, with the delta, if you can see it, it's kind of small. The different dashed lines corresponding to basically how much noise they had. So the more noise they added, the worse overall accuracy that the algorithm achieved. Lo and behold, who would have thought? I believe, yeah, that's pretty much the end. Summary is just basically, machine learning is hard and there's a lot of stuff going on. And in general, quantum machine learning and classical machine learning are very similar. The ways, sort of the tools that you use and the thinking that goes behind them are almost identical. It's just the hardware is different. And there's a lot of potential for quantum machine learning to be better than classical machine learning at certain things. And it's kind of the goal of everybody to figure out if that's really true. And just like quantum computers are to classical computers, it is extremely unlikely that quantum machine learning will entirely replace classical machine learning. Rather, they're probably going to end up in a sort of like mutually symbiotic relationship where one of them is good at some things and another one is good at other things. And you could even maybe get to a state one day where you have a machine learning algorithm that like does some of its training on a classical computer and some of it on a quantum computer, and they kind of intermix between the two. So yeah, questions? Yes.
Yeah, what are annealers?
Okay, yeah. What are annealers? Okay, how do I want to explain this? So you have the idea, it was basically taken from like annealing in metal, which is you take a metal and you heat it up to get like you have atoms, and atoms have grain boundaries between them, which is basically like stress points. And the idea is that if you heat up your metal, you'll these atoms start vibrating and then they break all these grain boundaries. And if you cool it down slow enough, you'll get very few grain boundaries, which means you have a much stronger metal. So similar process in the idea of like cooling, but nothing is actually like you're not heating something up and cooling it down. What you're doing is you take your problem, like there's an end state that you want to get to. And so you start your quantum computer in a really simple state, and then you just really slowly change like qubit by qubit until you can get to your end state. And the idea is that if you do this slow enough, if you start in the ground state of your simple, like encoding, you'll end up in the ground state of the answer, which is ultimately the real answer you want, because like a higher energy state is sort of useless to you, because it's basically in machine learning context, the ground state is like your highest accuracy and the higher energy ones are like worse. The specifics of it, like you get to, it's like, oh, well, you encode a Hamiltonian and you change the Hamiltonian slow enough depending on the energy gap, and there's sort of a lot of technical details to it. But yeah, the other thing is that you, that's sort of annealing like with it is as it goes on, like when you run an algorithm on it, you kind of monotonically decrease the probability that any qubit flips. So it's like there's a lot of changes happening at the beginning, and then as it gets colder, meaning as the algorithm runs longer, they flip less. Yes.
When you say slow, like in what order of magnitude are we talking? Like
it depends a lot on the problem. I mean, because it's literally, okay, I'll try to get a little more technical without getting too much technical. So the energy and time are related by a form of the uncertainty principle. And so you can basically think like, say you're in the best answer, optimum answer of your like starting state. And like, this is the optimum answer. And then the next answer up is here. Like, this is the energy gap. Like, it's this much more bad to go from the optimum answer to the next answer. you can change this a lot faster than if your optimum answer is here and your best answer is here. Because when you change this really quickly, you'll no longer be in your optimum answer and you'll be in your worst answer. So like the actual time, I mean, I guess I can say they typically run microseconds, I think, nanoseconds or microseconds. I want to say microseconds. Like tens of microseconds is how long it takes for a D-Wave computer to do some amount of annealing. But it varies greatly depending on specifically like the energy gap between the lowest state and the next state of at any given time.
So you're not annealing over the course of a couple of seconds, it's like microseconds.
Yeah. And it's not like super great. Like it's pretty typical that you'll get to the end and then it's not in the ground state. Like ideally, there's this thing called the adiabatic theorem that says like, oh yes, if you start and do this slow enough, you will end up in the ground state. But that's true for like the theoretical perfect quantum computers that are completely isolated from everything else and you don't have to deal with like thermal fluctuations. But as soon as you have anything else coming in here, it's sort of anybody's game if it'll be in the ground state. Yeah, go ahead.
So it's like one of the main problems is just keeping energy from coming in because
Yes.
energy you have, you know, very
Yeah.
it's easier to go up.
Yeah. No, keeping these things isolated, and this is true for all quantum computers, but especially for annealers, keeping these things isolated is like 90% of, I shouldn't say 90%, but a large amount of why this is so hard. Because you're dealing with things that it's like even a little bit of energy can drastically change your state. And you're like, okay, I have to keep like a photon from coming in here and completely ruining my machine learning. And you're like, okay, how can I block every photon? You're like, oh, I could just shield it with black stuff. It's like, oh, well, it's not blocking UV or IR, or you like there's suddenly all these considerations you have to take into account, which is why current quantum computers aren't that great. Any other questions? Yeah, go ahead.
Would you say materials chemistry would be very important?
Materials chemistry?
Yeah, so you could have something that would both be outside room or
Yeah, and like IBM's quantum computer, they put it in this, what is it called, a dilution refrigerator, right? They put it basically in this like the biggest fridges in the world now are just made to like store a chip that's this big, and you know they're like the size of a room. It's like 2 people tall and like tree trunk around. And the idea is it's just like you need to keep this thing as absolutely cold as possible. And then like around that, you also have shielding from other things like non-thermal, like photons, whatever. So almost certainly, yeah, the shielding would be super important. Okay, I think that's it. Here's that list of resources I was talking about before. We'll send out the slides and these are all great. Scikit-learn has a really good user guide. I just threw this one on there. I used it a little bit making this presentation. PennyLane is super good, specifically for quantum machine learning. Here's a link to my package. And then here's the paper that was talking about the QMLZ. So yeah, thanks for coming out. Yeah, we'll release them on the Discord, yeah.
And this will be also.
Yes.